Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, and thank you for coming to our continuing lecture series in software engineering. I'm John Devon. I am responsible for the engineering strategy group at Microsoft, and if you haven't heard of that, you've heard of Engineering Excellence, which is the initiative that we run across the company. I'm very, very glad to have the opportunity to introduce Mary Shaw, the Alan J. Perlis Professor of Computer Science at Carnegie Mellon University, a very distinguished speaker we have today, and really a leader in the computer science community in design and architecture. And it's great to have her come and speak to us. Where to begin? She got her PhD at Carnegie Mellon in 1972. From 84 to 87, she was chief scientist of CMU's Software Engineering Institute. Her research interests are very deep and diverse, involving engineering and programming systems, programming languages, software architecture, abstraction, really done a lot of very interesting thing, including program language design of a language called Alphard, which is a very interesting thing. In 1993, she received the Warnier Prize for contributions to software engineering. She's a fellow of the ACM. She's the member of IEEE and the Association of the Advancement of Science, and also a member of Sigma Chi. And so I invite you to extend a warm welcome to Mary Shaw. Thank you.
Well, thank you, John, for that introduction. Thank you all for inviting me. And hello out there in television land. I decided to talk today about something that I actually haven't talked about in public yet, and so we'll see how this goes. I'm interested these days in how you can predict value from design. The thumbnail is that we need better ways to analyze a software design and predict the value of its implementation. That value in the eyes of either the producer, that is to say Microsoft, or the customer, that is to say all those guys out there who send money in. And when I say analyze a software design, I'm particularly interested in the case where you can analyze a design and discover things that will become problems in the implementation if you implement it. And to do this before you actually make the investment of time and resources in getting code out there. So I'm interested in the kinds of analysis that you can do before you spend a lot of time coding and testing. I'm motivated in doing this by having thought about engineering design and the way engineers accomplish implementations and designs. After all, if you're designing a bridge, you can't go and put steel in the ground and then test it, at least not cost effectively. So they have stronger economic incentives than we do for doing the analysis before the implementation. But I think that looking at the way they do business offers good lessons to us. Engineers begin by iterating through a lot of high-level sketches of design alternatives. They do preliminary designs. They understand that each preliminary design costs some time and effort to create. They still do a number of them at a sketch level and decide which of those is likely to be the most promising if you pursue it to its completion. And then they do some refinements of that and evaluate those alternatives and continue on down through detail. As they go along, they work with the client to understand not just what's in the explicit requirement document, but what other constraints the client has that arise from business, from the context of use, or from other intangibles. As they do this, they think about the cost and utility of the design of the implementation and of the product in use, as well as the capability. And they understand that early decisions that they're making at these very preliminary stages where they're doing the generate and test can have a very substantial effect on later costs. Okay, this is an attractive way to do business, you might think. But in software engineering, we tend not to do that. Software development methods tend to pick up at the let's draw pictures of the way the system's going to be organized and proceed in a more or less linear fashion. And yes, I understand there are points of feedback loop in all these processes, but they're strongly linear and straightforward as you go down to design. It's hard to fault software engineers for not doing generate and test early on. It's easy enough to generate, but we don't have very good mechanisms for test. So we don't have a lot of good techniques that are well integrated into the software development processes for analyzing the designs to predict the properties that implementations are likely to have, for designing for diverse sets of users who have diverse preferences, and for including cost as an upfront first-class design consideration right up there with performance and functionality. We do know, though, that there's a premium for making for avoiding problems early. Bain and Basili suggest that fixing problems after software is delivered can cost 100 times more than fixing the problems and requirements in design. They suggest that up to half of the development effort goes into avoidable rework. This is a little bit self-fulfilling because avoidable rework is the effort spent fixing the problems that they think you could have fixed earlier. And so that's entirely consistent with this factor of 100 up to. And they also find that early reviews can catch most of the errors. So even in the absence of tools, peer-to-peer reviews can prevent some errors from creeping in. And then in the Kokomo 2 description, Bain provides a chart that takes a handful of data points and draws a nice curve through them. So think of this as evocative rather than definitive. But he points out, think of this data as confirming the intuition that as you get farther and farther toward implementation and deployment, your estimates about the size and cost of software get better and better. But if you put these things together, that there's an advantage of catching things early and that you get more information as you go on, that starts to suggest that looking for ways to get better information early would be to our advantage. There's another phenomenon that some of you may think of as common knowledge over here in the business side of the house, but I learned it from an engineer, and so it sticks in my mind as an engineering observation. That engineers make irreversible commitments despite that uncertainty, the uncertainty in Barry's chart about your predictions being very loose. So we have a tendency to think about spending resources over time as this S-shaped curve where the cumulative costs rise faster after we get down into implementation and staff up and start building things. But in fact, what the engineer taught me is that if you're looking at the cost of a project, the important thing to understand is when the costs were committed. And his point was that this was a chemical engineer, and in a chemical engineering construction project, that the decisions that you make in the first month are decisions you're going to have to live with through the duration of the project. And those commitments are shaping the cost profile. And so there's an additional incentive to make good decisions early because you can't back out of them later. So what about software? Well, we have a lot of techniques for analyzing code, and especially techniques for analyzing the correctness and the performance of code. They depend on having code, which you don't always have in early design. We have fewer analysis techniques for design. I don't want to even suggest that we don't have any, because there are a lot. There's architectural analysis, model checking, various kinds of cost prediction for the production process, things that will predict performance, and so forth and so on. And there are, incidentally, other situations where code isn't available. You may be working with COTS systems where the code is proprietary, and all you have is some proxy for what the code will do. And many development projects are incremental development over large legacy systems, and yeah, you have access to the code, but there's so much of it that the code analysis is intractable, and you might as well not have it. Or a slightly less strong statement would be, even though you have it and can analyze it, you can't get all the information that you need by analyzing the legacy code, and having the ability to make predictions on some basis other than the code would be to your advantage. So the current state of affairs seems to be that most of the evaluation techniques focus on the properties of the software products or on staffing and schedule. They don't focus systematically on costs. They don't use a whole lot of design information. And so as I go, you will see that I am saying we're going to analyze a design, but the only thing we know about the design is this very small piece of information. I'm being as generous as I can about what constitutes design. We spend relatively little attention to evaluating designs, although we do have this evidence that changing things early in design is less expensive than changing them later. And the techniques that we do have don't share a worldview. They're hard to teach, they're hard to explain, they require different kinds of specialized knowledge. They're non-interoperable both at the conceptual level, that somebody who understands one may not be willing to invest the effort to understand yet another, and at the implementation level, their formulations are put together differently. And it reminds me a lot of the 1970s when we were talking about how software tools don't interact because the output of this tool cannot be fed in as the input to this tool. You have to manipulate it manually to convert it. So what I want to do today is take the proposition that we should be thinking as software developers about producing value, not just about producing capability. That means that we have to think about costs of production and costs of use, that we have to think of benefits to some client, either the producer or the consumer, and that by thinking about value rather than just about capability, we'll bring into the software development process a set of considerations that have been neglected in the past and that would stand us in good stead. And I'm going to do this largely by doing two things in parallel. One is by talking through some techniques that we do have for predicting value from design. Now, I'll draw these from a variety of different areas. And to stitch these examples together, I'm going to show you a sketch of a framework that I've been nibbling around the edges of for a few months that might help us with the interoperability problem. So I'm going to run these two pieces together. So economists have a view of value. A firm's goal is to maximize total revenue minus the cost of input. And I'm collaborating with economists on this, and this text has been vetted and approved by the economists. I'm not going to read it to you in detail, just those of you who have seen the economists talk about this, this is where we're starting. Value is benefit net of cost. The objective of the firm is to maximize value, with the constraint that we're only maximizing value over things that are in a feasible region, that is, things that we can actually accomplish. So it's probably more familiar to see a graph rather than the equations. And the common graph is we have two products. Those are the outputs. That the inputs are limited because the capacity of this is input 2. Input 2 can be deployed to produce either product 1 or product 2, and you have to decide how you're going to deploy it. Input 1 similarly. For simplicity of modeling, the economists have always said these constraints are linear, which you know isn't true in practice, but it's a good first approximation. And then the feasible region is those things you can actually produce given the limits of what you can do with each of the various inputs. You couple this with what people like. This is a utility curve or a curve of indifference. and these are not linear. This says that a typical user who has a lot of one thing will value an extra unit of that one thing a lot less than a unit of the thing they haven't got much of. And so this says that if I have a lot of product 2, then, do I get the mouse? Yes. If I have, if I have a lot of product 1, then the incremental value of product 1 is a lot less than getting some more of product 2. And as you get more and more, the lower line is less valuable, then the next line is less valuable than the line above, than the line above it. And so these pictures are saying that I'm indifferent on any one of these lines, but as I go up and to the right, I'm happier. So this is the basis of linear programming and other techniques that you learned in your economics courses. And even if you don't actually write the equations, this kind of intuition can be helpful in deciding what kind of mix of capability to put into a project. So now I want to run through some examples that emphasize what can you learn without looking at the code. So my target is to try to go after very high-level design, what the engineers would call design, before the software design methodologies, so-called, start writing box and line diagrams and elaborating those. I'm after evaluations that consider not the product in isolation, but the product in light of what a particular user will like about it, or will value in it, or will be willing to pay for it. So I'm going to do examples from the standpoint of the consumer. You can do a similar set of analyses from the standpoint of the producer, but for the sake of consistency, I'm going to take these from the standpoint of the user. These evaluations need to weigh both the costs and the benefits, and I'm particularly interested in evaluation that doesn't depend on access to the code, because I think that is a critical property of evaluation done early. My long-term objective is to try to develop a framework that allows us to unify these models, that is, to make them interoperable. So it needs to be general enough to accommodate specific models. It needs to be open-ended so that more stuff can be added. And it needs to accommodate estimates at various levels of detail and precision, because in the act of doing an evaluation, you're actually doing, at least intuitively, a cost-benefit trade-off. I'm going to spend 3 days developing this model and doing this analysis. What else could I spend those 3 days doing? Am I going to learn enough from doing this analysis to justify it, or should I spend those 3 days doing a different kind of analysis? Or should I spend those 3 days generating code so we can test it? So the basic value proposition is you figure out what the benefit is, you figure out what the cost is, and that's your value. The simplest example that I could imagine was I have the choice to buy a software tool for X dollars. It will save me Y dollars right away on my current project, and then I'm going to throw it away. The value is Y minus X. If it's going to generate more value than cost, I should buy it. Okay, so much for simplest example. More often, we're interested in the value of a design. And so the trick about designs is that what we're interested in is the value of the implementation, and what we have in hand is the design. So I want to treat an implementation as represented by a property list of its various capabilities. And this is one point at which the framework is extraordinarily open-ended. The property lists are anything you happen to be able to derive. So think of these as a sequence of attribute value pairs. The types of the values are as appropriate to the attributes. This is just a long property vector. This is cast at the moment as the capabilities are expressed in the rationals. That is a limitation that we'll see as we go along. It gives you a little bit of analytical tractability, but if you hold to that, it excludes some analysis techniques. The value space is explicitly multidimensional because the values may come in the form of convenience as well as dollar cost. in the form of performance as well as dollar cost. And I'll argue later on that converting all those immediately to dollar cost is a bad idea. So the evaluation of V equals B minus C is done in a multidimensional value space. The implementations are represented by capabilities. So an example of trying to understand the value of a feature, that is evaluating B of X or C of X, was done a few years ago by a couple of economists who asked, what is the value of features in spreadsheets? And they actually do a fairly detailed analysis of particular features in spreadsheets. But the broad brush results were that there are some network externalities that, in addition to the specific features that lie within a spreadsheet product, that a 1% increase in the installed base of that product leads to a 0.75% increase in the price of the product. That is, having more people with whom you can exchange files, more people to whom you can go for advice about how to use it, conveys benefit to the consumer, and their analysis quantified that benefit. They showed that adherence to the dominant standard generates a very substantially higher price. This was done in the spreadsheet market of 1987 to 92, so do not take these numbers as current numbers, but take the analysis as a kind of analysis that tells you something about what kind of product you might want to produce. They found that the quality adjusted price over 5 years declined 16% per year. That is less than the Moore's Law decline. And they took a restricted model that they call a hedonic model, which is basically reductionistic. It says that the value of the product is the sum of the values of the features. You can find all kinds of fault with that model, but they found that the model was a good approximation for doing this kind of analysis. So this is not an automated analysis. It was not a simple analysis. The paper is out there. But it says that if you are interested in things like, there's a huge market out there, how should we position our product in the market, that there's a kind of analysis that will tell you something about these strategic design decisions that you can actually quantify. Now, one of the things that is inherent in trying to understand the properties of a design that will subsequently be implemented is that there is uncertainty about the values. Bain's chart about decreasing uncertainty as you move toward implementation suggests this. You also know that there are vagaries about what may happen in the future. And I want to pick up particularly here the very easy analyses about future values of money. And I'll say something later about doing this for risk. So here's an exercise that I give to my students when I'm trying to get them to understand that value now is different from value later. This is Finance 101, and it's a very simple net present value problem. So should I purchase or license a component? Well, the benefit of having the component will be $60,000 a year realized at the end of the year. The license cost, if we license it, will be $50,000 a year due at the beginning of the year. The purchase cost will be $120,000 payable now, and we'll assume an interest rate of 5% per year. And the exercise is, so what happens year to year? Which is the better decision? Should I buy it or should I license it? And I ask them also, how sensitive is it to the interest rate, which isn't shown here. So the table says there's 3 columns for the actual prices. There's a column for the present value deflator. Then there's another set of 3 columns that says, okay, if you apply the deflator, what's the purchase, the present value of the purchase, the present value of the license, the present value of the benefit. There's one that accumulates it, and there's one that does the subtraction. And so you can see in the last 2 columns the relative values of licensing it and purchasing it. There is nothing profound here. It's just an exercise that sometimes people find revealing, that reminds them that value later is not the same thing as value now. The significance to the question of value computation is this: it reminds you that not everything is this simple, but that you do need to incorporate in analyses the possibility of doing the analytic adjustment for risk. This is a point at which the interoperability of techniques comes to the fore. So many techniques that we have for analyzing value do not do any time dependencies. It would be nice if we could compose neatly the analysis for time dependencies with the analysis of other properties so that we could get the leverage by composition rather than by immediate action. Erdogmus lays out a half a dozen points at which present value issues arise in thinking about a software project. His image says, let's take the simple view that a software project has a development period and an operation period. There is a cost of development, which is usually figured as a present value at the current time. Then there are costs of operation and maintenance, which you tend to think of as having a present value at some time in the future. There is a flexibility value that measures some enduring, possibly implicit value of strategic flexibility throughout the lifetime of the product. And risk is a discount factor that takes the operation costs and moves them back to the present so you can actually do the comparison. And so in this view, the net present value of a project is the value in operation deflated to the present minus the investment in the development plus the value of strategic flexibility. And again, that's a fairly simple model, but it's got elements that remind you of other things that you might work into the analysis. So what about this discrepancy between having a design in hand and wanting to evaluate the effect of its implementation? We're assuming that we're looking at the situation where we don't have code, and so we need to predict the implementation properties. Well, the implementation properties are going to depend not only on the design, but also on the method by which the design is implemented. Many times the implementation properties will depend on that. So I'm going to add a term that says we're going to get the properties by making a prediction from the design and the implementation method. And the implementation method I will take to be in some notation that is convenient to you. And we're going to add a predictor that tries to predict the capabilities that method M will deliver for the design. That's a D hiding over there in the corner. One of the ways we do this is by looking at formal models. So the example that is most familiar to the most people is analysis of algorithms, which tells you the running time, how it will scale with respect to problem size. Now, all the analysis of algorithms models assume a competent implementation. So many sort algorithms are analyzed formally to be n log n algorithms. I have taught a number of these at various times. I remember very vividly one day when a student turned in an implementation of one of the standard n log n sorts, and I didn't understand it and spent a couple of hours wrestling with it. And I am pretty sure that this particular implementation ran an order of n cubed. It was one of those guys that has some bounds within the array that shrink down, and the reason you're getting the n log n is that the subsequent searches are carried within a range, which then subsequently gets reduced. I mean, you know the ones. Well, he wasn't dealing with the bounds right, and so the comparisons were running up and down the array all the time. Okay, so all these analyses that say it's an n log n algorithm are assuming a competent implementation. And if it's a competent implementation, then you get the performance that you expect. So here the design is the pseudocode of the sort algorithm. The capability in question is the order of n log n scaling, and note this is one point at which saying that the x's are taken from the rationals breaks down. The value space has to include a scalability term. This is silent on converting how much n log n-ness is worth to the client. That's a separate problem, and another point at which we need to be able to do a composition. I think it would be a really silly idea to try to fold benefit to a particular client into a well-formed discipline of algorithmic complexity. But we do need to compose this outcome, order of n log n scalability, with something that will say, how do I figure out whether I care about n log n scalability? The development method is the programming technique of your choice in the hands of a competent programmer, and we're predicting the expected runtime. So I could have done an example here involving model checking, but it's easier to talk about the algorithmic complexity model. So there it is. Okay, so what about that cost term? Well, I want to add 2 more parameters to the cost term, because even to the client, cost includes not only the cost of the capabilities, but the cost of doing the development. And for a client to be able to evaluate the benefit of a system, a client often needs to evaluate how much he's going to pay you to develop it. And so I need to enrich the model to reflect that. So I'm adding the design and the method to provide access to that information to the cost evaluator, to the value of the system evaluator, as well as to the predictor of the properties of the implementation. And to do that, another familiar example, is this a familiar example here? Is Kokomo familiar in this world? Kokomo is not familiar in this world. Okay. Kokomo 2 is, unsurprisingly, the successor of Kokomo 1, which was actually called Kokomo because there wasn't a 2, and so you didn't need to call it a 1. Kokomo arose out of some empirical curve fitting to development data at TRW. And the original Kokomo model said man months, now called person months. Man months is equal to some constant times the size of the code to the 1.0 something power. And the purists among us will look at that and say, nothing in nature is to the 1.0 something power. What's going on here? The pragmatists among us will say, I'll bet it's linear with second order terms or something like that. And the real question is not whether it is exactly right, but whether it tells us things that are worth knowing at a price that's worth paying. And the answer to that seems to be a resounding yes. So in refinement, Kokomo 2 includes not only the successor to classic Kokomo that is applicable when you're actually generating code, but a handful of variants for other situations. And the situation of interest here is early design. So there's a simplified form of Kokomo that applies in early design when you haven't got code, which is exactly the situation we're interested here. Kokomo predicts effort, called person months, and schedule, called time to development. The equations are essentially similar in the 2 cases, and so I'm just going to carry time to development around as a variable. If you opened it up, you'd see the same things. It's just not worth grinding through the same thing twice. So the fundamental equation is that person months is A times the size of the program to some power times the product of some effort multipliers. And that exponent, for typesetting reasons, is split out in a separate clause. That effort is some other magic constant B plus 1% of the sum of some scale factors. Now, what are the effort multipliers and the scale factors, and the A and the B? Well, it's pretty well established for all the variants of Kokomo that you get a certain amount of benefit if you use generic numbers that have been created by curve fitting to an assortment of projects. There are 161 projects in the database that are in the book. That you can get more value if you invest in calibrating these numbers for your own internal processes and your own internal development. Another clear case of a cost-benefit trade-off. Are you getting good enough predictions with the standard numbers, or is it worth it to you to have more precise predictions in exchange for the cost of recalibration? So the A and the B are magic curve fitting constants. They come to us courtesy of statistics. The effort multipliers and the scale factors are essentially similar. They're called different things because they sit in different places in the equation, but they characterize the project and the project developers. Is this a project you've done before? Is this an isolated project or a highly embedded project? Is it on a platform you're familiar with? And other things, mostly about the internal processes. You rate them on a high, medium, low scale, actually a very low, or extra low, very low, low, nominal, high, very high, extra high scale. It's a 5 to 7 point scale. And you get some text guidance about how to make those selections, and once you have done so, there's a table based on the 161 projects or your own calibration that converts these things to three-digit numbers, which you can then add up and multiply together as indicated. So this is still the basic effort is size to constant time size to an exponent model, but with some tuning about how you select the constants. And so as Kokomo has evolved over the years, I've been interested to see how much structural knowledge about the process is being worked into the model. And I think Kokomo itself is an interesting example of the evolution of an empirical model into a more principled model. Well, the thing about Kokomo is that it depends on knowing the size of the implementation. But the lines of code aren't known early in the process. So the interesting thing about the early design model is it says, well, how we're going to get the lines of code is we're going to look at the requirements and count the function points. So you know about function points? I'm not going to do an excursion into function points. Function points are basically feature counts. So you do a count on the requirements for something that you might actually be able to extract from the requirements. That yields a number called the number of function points. And then there's a table that says if your programming language is this, then a typical function point converts to this many lines of code. Okay, now notice that there are three predictors here, and they are composed. So there's a predictor that goes from requirements to function points. That's exercised manually. There's a predictor that goes from function points to lines of code. That's a table that's been calibrated. And then there's a function that goes from lines of code to staffing effort. So composability of these models is possible, but this was not an ad hoc construction. Is that enough about Kokomo? It's a predictor of effort. Well, one of the interesting things about Kokomo, when I went back and looked at it, is that most of the effort multipliers and scale factors are actually describing the development method. But three of them kind of stick out like a sore thumb. And the reason they stick out like a sore thumb is that they're not about the development method. They're kind of turned around to look like they're part of the development method. You've looked at these, haven't you? They turn around to look like they're part of the development method, but they're really about what you're trying to produce. They're the required reliability and complexity, the required development schedule constraint, that is, what's the drop dead date from the client, and the required amount of reusability. So these are product capability targets. And I have restated the early design estimators in that equation to retain these things as parameters. For simplicity, I'm only going to use two of them for a reason that will become evident in 2 or 3 slides. So if I do that, then I can map it into this framework. So the product capabilities are the reliability and schedule requirements, which are drawn from extra low, very low, low, nominal, and so forth. And this allows me to say I'm looking for a predictor of, in this case, the amount of effort that will be required to produce a system that has these properties, assuming you can do it at all. The only thing I've got about the design is the size. I told you I was going to be generous about what constitutes a design. So we have the requirements went to function points, that yields a size. It's a pretty puny description of design, but it's what we've got. The value space in which I'm going to say how good is this is going to be the development effort, person months, the time to development that I'm ignoring here, and these two product characteristics. And the method of development is encoded in the calibrated constants A and B and the particular selection of values for the other effort multipliers besides the two that are my implementation target and the scale factors. And so then restating the equation, all I've done in the equation is take this product and take this product over everything except the two that I care about, and then explicitly multiply those back in. And this allows me to deal with it symbolically. Okay, bear with me now. You don't really need to follow all the steps. But what I'm saying is that if I want to evaluate the cost is the cost of, recall, the cost of the design, the capabilities, and the method. So here's the cost of design. These are the capabilities I'm after, and the method is represented by these four terms, per the previous slide. And it's going to come out in a space that has development cost, time to development, and these two properties as their results, and now I start substituting. So the person months is, here is the formula for the previous slide, and the other three terms are unchanged. I can now take the size from the function point composition, which is all of this stuff. And then if I just take the nominal values from the model for all of these constants, I could obviously do other things, but we're trying to make progress here, right? Then all of this reduces to 2.94 times size lookup of the function points to the 1.09997 power times these two terms with all those other things. And then if I pick a size of 100,000 lines of code, just for the sake of making some more symbolic terms go away, then my answer is 465 times these two constants for the person months, plus these other things. So what does that actually mean? Now you see why I only wanted two terms, because now I can show you the trade-off space for how tight is your schedule versus how much reliability you're asking for. And what I've done is take the COCOMO equations, turn them inside out, and I've delivered something that says, here is a space where you can think about how much reliability and schedule flexibility you're willing to pay for. So this says as you go from low requirements for reliability to high requirements for reliability, the effort goes up. Big surprise. Similarly, schedule, very low means a very tight schedule, and very high means we're relaxed about the schedule. As the schedule gets tighter, it goes up, but it doesn't go up as fast with schedule as it goes up with reliability. So that's the kind of insight that you can get by taking a predictive technique and pulling a couple of things out of it and solving for the variables of interest. Okay, the next thing that should by now be unsurprising is that the capabilities are multidimensional. They may be measured on different scales. In other words, measuring time is not the same thing as measuring money. And although there's some interconvertibility between time and money, it's not complete. And I want to make a case that you should resist the very strong temptation to look at everything that might constitute a cost and reduce it to dollars immediately. So the summary of the case is that there are different factors in a problem that are appropriately measured in different ways. We have dollars. We have computer resources. And there are different kinds of computer resources. Battery life and bandwidth are not the same thing. An important thing to measure in things delivered to end users is end user distraction. That's a resource that is too often discounted by producers. There's the staff time for production, the reputation of the company, schedule, lives lost. You get really, really bad press if you're caught converting lives lost to dollars in planning. I mean, I understand it happens under the covers, but it makes really bad press. The automobile company only valued a human life at, it doesn't matter what the number is, it's the only that matters. So if you turn everything into dollars, then you lose information about constraints that arise because not everything is convertible to dollars. You introduce errors by treating things that are not ratio scale numbers as if they were. You lose flexibility of analysis by doing early binding. This is partly a lazy evaluation argument. and you may confuse precision with accuracy, something that's easy to do. Sometimes you come down to the wire and you have to say, is it going to be A or B? At that point, you're going to have to do some conversion. But if you retain the information, then you can rethink that conversion later without redoing the analysis. So I say not all resources are the same. Here are some examples. The terms come to us courtesy of the economists who have thought about this in other kinds of production situations. Perishable resources are lost if they're not used. Bandwidth, for example. If you don't use it now, you'll lose it. Disk space is non-perishable. If I have extra space on my disk now and don't use it now, I can use it later. There are fungible resources that can be converted to other resources and some that can't. So common currency is important economically because it is highly fungible. There is partial convertibility, for example, between bandwidth and CPU. If you do compression, then you're spending CPU in order to reduce the bandwidth requirement. And then, as Brooks told us as long ago as the first edition of the Mythical Man Month, calendar time and staff months are not interconvertible. That's the more programmers make it later phenomenon. An important characteristic of the software market is that some goods are rival goods, that is, if one person has it, somebody else doesn't, and some are non-rival goods. The information goods that we deal in are non-rival goods. If I give you my information, I have it, and so do you. And that's why piracy is such a problem for information goods when it's not for physical goods. It's harder to replicate a book than it is a file, because a book is a rival good. I have the book, or you have the book. If you want us both to have the book, somebody's got to find a way to replicate a book, and that will have cost. We also have the problem that not everything is measured in the same terms. Is this a familiar set of concepts? Okay. It's 60 degrees outside today. It was 30 degrees outside yesterday. It's twice as warm today as it was yesterday. Right or wrong? Fahrenheit isn't zeroed at absolute zero, and so it's wrong. If you want to say it's twice as warm today as yesterday, you've got to go back to absolute zero. So it was 283 degrees yesterday, and it's 343 degrees today, and so it's 343 283rds as warm today as it was yesterday. You can say that, although it's not nearly as impressive. A common problem that you run into is doing preferences on a 5-point scale. I don't like it at all. I don't like it a little. I don't care. And then calling those 1, 2, 3, 4, 5 and starting to compute averages. So I don't want to spend a lot of time doing Measure Theory 101, but I do want to remind you that just because you have ranked things in order doesn't mean you can compute arithmetic on the orderings. And this is another factor in the need to maintain a vector of values rather than immediate conversion. So my next point is that particularly in the frame that I've set here, where I'm talking about value to a consumer, value is in the mind of the beholder. And when you put a product in the market, value is in the mind of the consumer. When you put a product in a market other than single client bespoke software, a product may have many different values for many different consumers. Now, one of the things that I've learned in research settings that are not represented in this particular talk is that the gold standard of specification, that the specification of a component is all you know, all you need to know, all you may know, that has a lot of merit for development and analysis, but there's a big discrepancy between that and life in the real world. Because real people depend on both more and less than you're promising. Think about a subroutine library. I care about trig, you care about strings. If the trig works, that's all I care about. Strings can be completely broken and the subroutine library will be just fine for me. If it's strings that are broken, You may not care about trig, which is fine for me, right? So now we've got very different values for the same object. It's also possible, as I'm sure you know, for users to depend on things that you hadn't promised just because they've noticed in examples that it happens to be true. So the expectations of a user may not match up with a component-centered specification. And I understand that it's already hard to deal with component-centered specifications that consider only the component. But I think there's a reality out there that says that the problem is even harder, that you need to deal with the user's expectations as well as with the component specification itself. My poster child for an example of depending on something that wasn't promised may be apocryphal, but when I was very young, I was told by friends of friends, because I would never do anything like this myself, that if you wanted to place a numbers bet with a bookie on the corner, right? This was before the state lotteries. If you wanted to go down to the corner and place a bet with a bookie on the corner, the way you figured out whether you hit the number or not was that you looked on the New York Times at the last 3 digits of the volume of the New York Stock Exchange. So you didn't have to find the bookie to see if you hit. You didn't have to trust the bookie to see if you hit. There was a public neutral arbiter. I am quite sure, whether the story is apocryphal or not, that the New York Stock Exchange never intended the affordance of supporting the daily number as part of their announced volume. I have also been told by friends of friends of friends, because you know I would never do this myself, that at some point the New York Times became aware of this and they started rounding the volume numbers to the point that they were no longer effectively random. Okay, so you put a system out there and people will depend on some affordances that you hadn't anticipated. Value is in the minds of the beholder. Well, if we're going to evaluate value in the minds of the beholder that way, we need to find a way to express value in the mind of the beholder. And so the last term I'm going to add to this today is to add a term called theta courtesy of the economists that expresses the user preference in this multidimensional utility space or value space that we're using for subtracting C from B and getting V. As cast, I'm adding it to the benefits but not to the costs. There is some discussion within my research group about whether it needs to be reflected in the cost as well. And for purposes of the discussion today, I don't think it matters. It does need to be there as part of the benefits, because the benefits that are touted by the salesman may not be the benefits that the user sees. And the user's decision to buy is based on what the user cares about, not what the salesman cares about. So I have a student who is about to make a thesis proposal, who is working with my colleague David Garland in the domain of utility-based adaptive configuration in the world of mobile computing. So the game is mobile systems, your cell phone, your PDA, even your tablet, are resource limited. They're intrinsically resource limited because they have limited processor power, they have limited battery life, they have limited storage capacity. And they're also limited because they move from environment to environment where the resources may come and go. So if you're moving around a mobile environment, the bandwidth will change as you move from place to place. External systems that you may be depending on for content will also change as you move from place to place. So the setting is that mobile systems are resource limited, and also that different users require different capabilities at different times. Editing email, viewing movies, doing mapping, finding restaurants, all these are of interest to the owner of the handheld at different times, and the preferences about the quality and quantity of service may also vary. So for example, if I am sitting in a quiet place enjoying a cup of my favorite beverage, listening to a symphony, I may care a lot about the audio fidelity. If I'm just using an MP3 player to drown out the noise of the airplane, video fidelity isn't so much value to me as having something that will distract me from the drone of the airplane engines. And it's the same me, remember? So one of the innovations in this project is that they're trying to do the adaptive configuration in terms of abstract capabilities or abstract tasks that the particular user is trying to accomplish. So my abstract task may be navigating around a strange city finding a restaurant, or my abstract task may be doing a movie review where I'm looking at the movie, dictating, and doing text editing. So these bundles of capabilities are user-specific tasks, and you can support those with different collections of applications. Many different editors can be used for handling text. Many different, at least several different media players can be used for viewing a video stream. They have different impacts on the resources. They may have higher bandwidth requirements, they may have higher battery drain, they may do different things with the screen brightness because of battery drain. And the question is, for this particular user at this particular time, subject to the uncertainty that you don't know how long he's going to stay on this task and there are switching costs to go to the next task because you've got to shut down and start up applications, what's the best collection of applications to run now for some unknown duration to switch to some unknown task where some of those applications may be useful in the next task? Well, the first question is how do I do the point evaluation of what I should run now? That's not rocket science. But that's a place to build on when you start introducing the other uncertainties. And what Vahe is doing is using utility theory and the linear programming model, although it pretty quickly turns into integer programming, to find the best set and configuration of services for right now. And so here we are back to this question. If you're trying to run two tasks at the same time, one of them is looking up stuff from a database about local businesses, and it's not available over wireless, so you have to store the information and the GPS waypoints and things like that. And the other is I want to take some email on the road to process. I have enough memory to handle up to 50 map lookups or up to 20 emails to process per 100 units of memory, and I can have any combination of those I want, subject to half an email isn't going to be much use to me. But roughly speaking, I can pick any point along this line or close to this line. I also know that doing these things is going to consume battery life. I'll have enough battery life to do 40 email process responses if I don't do any map lookups, or 30 map lookups if I don't do any email, and I can pick other points along here. And so that means there's no point in attempting to load 50 map lookups and no emails because I've only got enough battery to do 30 map lookups. And so the situations that I ought to consider are in, guess what, the feasible region. And this particular user is okay with, 3 emails and 28 map lookups, or 5 map lookups and 18 emails, and a variety of other trade-offs. But of course would be happier with more of both, and would be still happier with still more of both, and would be ecstatic with some combination that we can't achieve because we're resource limited. And so the game is, which is the highest curve we can achieve, and where on that curve should we go? And the answer, of course, is right there at the corner. This is what you learned in linear programming in Economics 101. So for him, it comes out like this. The task model says there are 3 things we care about. There are the actual underlying resources like CPU and bandwidth. There are the capabilities of playing videos, browsing the web, and some other kind of service. And there's the abstract tasks that I'm trying to carry out. He gets, and then there is additionally the user satisfaction. So he gets 2 kinds of information. He gets application profiles about the underlying applications as to how they use the resources. Okay, there's a problem about how to acquire that information, but he's picking up at the point that you have characterizations of your applications that say, here are their resource consumption profiles. And he takes those and selects suites of compatible implementations that will accomplish a task. So he's he's worried about this part. He also gets information about user preferences, which again is a hard problem, and somebody else is working on it, to get reactions to particular combinations of capabilities on a scale of I don't like it to I love it. Whoops. Okay. And then cast into this framework, the emphasis of this work is on incorporating the value model of a particular user to say, what does the user care about? And to use an expression of the time-varying preferences of the user. So the implementation characteristics of interest are the qualities of the delivered service, for example, video fidelity. Another one of his examples is language translation. There's a little family of natural language translators around that have three principal components that can be mixed and matched in some but not all combinations. They vary a lot in their vocabulary size, their resource consumption, their accuracy of translation. You need one level of accuracy if you're saying, please, where is a restaurant, and a different level if you're trying to rewrite contracts. So there's another setting where you can do mix and match, and the best for the user depends on the user's current needs. So the design that he's looking at is the application configuration, that is a media player plus a translator, for example. And the value space is the user utility, the sequence of configurations you're going to produce, and the resource use that they're going to require. Then the game is to predict for a given application configuration what the capabilities are going to be, and the method is doing the configuration, which is not a big factor here. So the idea is to produce a tool that selects a sequence of configurations, that is, the design is the sequence of configurations being produced, and the objective is to satisfy the user's personal preferences as expressed. Okay, so that's the research task. And then back to this picture, what that amounts to is that the designs are the capability points in the space he's working in. The characteristics of the configuration are the service qualities that are delivered with the whole task. The user preferences come from those utilities, and what he's trying to do is to maximize the benefit of how good are all these configurations in the eyes of the user, and which is the best, or the closest to best that I can do with available resources. Because remember, you have to make these decisions without distracting the user, because that's another resource of interest. And if you say, please go away while I compute for 5 minutes, that doesn't win. Okay, so I said that I want to make the case that there's a lot of value in doing early evaluations of designs to see what kind of value they will deliver to their end users, that there are techniques of various kinds to address parts of this problem. I walked you through some parts of the problem, and now I can try to wrap up. So the underlying sensibility here is that software is, for the most part, produced for economic benefit. I have considered here the value to the buyer. You could do a similar kind of analysis that might be different in detail that will look at value to the producer. Certainly a given piece of software may have different values to the client and the producer. One of my colleagues and I spent a couple of weeks struggling over whether maintainability should be part of the characteristic space. Until we finally came to terms with the fact that we really were looking at different value functions for the producer and the consumer. The producer may place a very high value on maintainability. Most users don't. Most users are completely oblivious to maintainability. So you may actually consider different factors. But, back to economics, to have a basis for a market, you have to have producers who are willing to produce and sell for prices that buyers are willing to pay. It's only when you get an overlap in the willingness to buy and the willingness to pay that you actually have a market. And notice that the price is usually currency, that is dollars. But the price might be paid in peer respect, which helps to explain another phenomenon that we're not going to talk about today. Okay, so software product design, I am now asserting, should consider this economic reality for cases in which software is produced for other reasons than because it's a hobby and you enjoy doing it. I took you through 7 examples. There were 2 toy examples, that is, value is a simple subtraction, and finger exercise in present value analysis. I took you through 3 actual models. One is value of features through econometric analysis. One is performance prediction based on algorithmic complexity, and the other was cost of dependability and schedule constraint. It's a prediction from Kokomo. I also noted that there's a predictor that gives you lines of code predictions from by going from requirements to function points on the way. And I showed you a couple of pieces of current research, one about multidimensional cost analysis and one about user-oriented configuration of mobile devices. I could have picked many other examples. Here are 3 that I won't take time to dwell on, but my student Sean Butler gave a talk here about a year ago, I think, that talked about her security attribute evaluation method. The game is that every company has a different set of security concerns, and she has a method that uses decision theory techniques to elicit a particular client's threat and asset protection priorities. That is, she gets a theta for a particular user. She evaluates per threat countermeasure effectiveness using a strategy that includes defense in depth. And she can weight countermeasures by the priorities and come up with a ranking of the choice of what security technology to install next in your installation in terms of the kind of coverage and protection it will give you. She's a collaborator on this work, as noted on the title slide, and this is a topic that she's bringing to it. I can roll back in history to early cognitive modeling for user interfaces and many of the more recent incarnations of that. What's that 23 doing there? The cognitive modeling techniques for user interfaces say, let's start with a description of a user task and some fairly rudimentary estimates of how long it takes to do particular tasks, and then we can roll those up to predict the time that it will take to execute the task. So one of the triumphs of this was an analysis of Project Ernestine in AT&T. They were looking at a major reorganization of the directory assistance protocols, the things the operator says. The telephone company cares a lot about directory assistance because every second added to a directory assistance interaction costs them millions of dollars a year. That is not per interaction, but if an interaction takes a second less, it would save $1 million or so a year. And they were looking at a major revision to the directory assistance operator's protocol that had a lot of attention paid to making a lot of the tasks simpler. And my colleague Bonnie John got involved with them and did a GOMS analysis that involved, these aren't linear tasks, so it's not just adding things up, but you create a diagram that includes a critical path diagram. She discovered that they had saved lots of seconds on the non-critical paths, but they had added 2 seconds at the very outset, that is to say, on the beginning of the critical path. And her projection was that it would cost a lot of money. There was then a certain amount of discussion, and I believe that they eventually decided that she was right. So it may be a rudimentary model, but if it tells you important things, then it may be worth everything you put into it. Another example is the possibility of using real options to evaluate the value of delaying a decision. The intuition here is that sometimes it's worth additional costs now to preserve flexibility later. There will be some cost of exercising the flexibility later if you choose to do so. But that cost is presumably going to be less than the alternative, which is not having the flexibility and having to undo things. So an example to think about is reusable components. Should I make this component reusable? Well, we all know now that you can't just pluck it out of the implementation and set it on the shelf. You have to make it work in all the rest of the cases that you didn't care about. You have to provide some documentation. You have to make sure it aligns with the interaction standards. So there's a certain amount of cost you incur now to make something reusable. You're making this reusable against the hope that it will save you effort later. Well, if you take it off the shelf, there will be some cost of figuring out what it is, finding it, figuring out how to use it, and actually use it. You're hoping that that will be very substantially less than implementing it from scratch. And that the value might come in implementation time, it might come in future maintenance time because there's one less thing to maintain in the future. But you don't know when you're making the decision about whether to make it reusable, whether you're going to harvest that cost. So there's some work that's been going on to try to cast that in terms of the economic model of options. And I could map out the details, but I'm not going to dwell on these examples. I just rolled them up there to enrich the space. So I have two summaries of the talk. The summary for researchers is that there are lots of opportunities out there. We have opportunities like finding more techniques for predicting value early. I'm interested in trying to enrich the ability to harness these things together, to make them interoperable. Possibly by functional composition, as we saw the function point estimates roll up into COCOMO. Possibly by doing parallel evaluations that generate more terms in that value space so that there's a richer kind of analysis to do. And when you start doing that, you've got to think about the comparability of semantics across techniques. If I'm producing a performance number and you're producing a performance number, are we talking about the same kind of performance? Another thing that comes out of this is that we need richer ways to deal with data that doesn't come from the rational numbers. How do we combine estimates come from different places? And I am absolutely not going to dwell on that right now. And then I'm personally interested in refining this framework to try to make it a richer playpen for us to bring techniques together. If nothing else, I think the exercise of taking a predictive technique and casting it in this form will make it easier for people to understand what's available and what they've got to do to apply it and what benefit it might offer them. And so just from a standpoint of enriching our collective vocabulary of things that we can study, to ask people to pin down what it is they're contributing in some shared space, and I personally like this one, looks to me like a thing worth doing. Okay, what about the developers? Well, there are lots of opportunities here for developers without even waiting for research to turn out something. First, there is a lesson, and I hope I've provided you with some evidence to support it, that doing early evaluation of designs is valuable. I suspect that most good developers are already doing this now, at least implicitly. But by providing a little more explicit way to hold the discussion, I think the discussions can be more constructive. In particular, I think making it more explicit can help to draw in younger developers who have not had occasion to think about anything beyond what you called working in the box. Rob called it working in the box. Nothing other than can I make the technical capabilities better? To be able to hold a discussion that draws in people who haven't thought about the question, I think will benefit the design discourse as a whole. The current suite of predictors is not particularly well organized, but if you start paying attention to what's out there, there really are a lot of things out there. And if you pick the ones that are useful to you, you can get benefit from them now. But another observation is that if you understand the basis for the reasoning, oftentimes taking that intuition and applying it qualitatively will be cost effective. That is, it won't give you a lot of precision, and it may not be terribly accurate, but it may be a whole lot better than guessing. And the qualitative application of an analysis is something that you may be able to do over coffee, even, but certainly with a lot less investment of time and effort. So given that it's often relatively low effort, the amount of information that you get from doing it won't be perfect information, but the amount of information may be good return for the effort that you're putting in. And then there's the canonical, hi, I am a researcher, be of good cheer, there's more stuff in the pipeline, which I put here as a matter of obligation. So then finally I have a request. As you can see, I am collecting techniques that predict value, in particular from design descriptions that don't involve the code itself. I'm interested in things that predict characteristics of the implementation, and I'm also interested in things that can characterize user preferences, and in things that can go from characteristics of the implementation into the user's value space. And so if you know of things that I don't know about, please tell me about them. It would be really cool if there were something like a citation and an example of its use in practice, but just saying something like go and look at would also be helpful. So thank you very much. That's what I've been doing.
Thank you. It's probably time to take 2 questions and then we should shut down.
It's really the design known up front. So general design practically is represent a series of design decisions over the time. And actually each decision depends on a subset of previous decisions. And what worse is that time itself is a function of the previous decisions. So how you can incorporate this into your model?
So the question is implicitly, am I still stuck in the waterfall model with the assumption that I had the design up front? No. Look at the case of legacy systems where you're really designing an increment on the system. Your question then is, what's the value of the increment? And I absolutely agree that design evolves. It evolves not only as the implementation evolves, but also as the client's understanding of what he actually wants evolves. And many clients don't come in understanding what the technology is capable of producing from them, and so they can't be articulate about what they will turn out to need after they understand what's possible. I think actually that evolution makes it even more valuable to be able to make better predictions with less information, because you're not doing it once, you're doing it over and over and over. So there's a multiplier effect of any kind of leverage that you get.
Yeah, okay, quick question for you. I noticed on your request, you'd like to know more about how we're predicting properties. I was going to ask you, how do you do it? Because, we have product planning, which looks at and asks users quantitative analysis of how important is this feature compared with other features and so forth. What is your recommendations for books or theories behind this?
Well, if I had a really great systematic source, I would have given a very different talk. My understanding of the current state of the art is that there are a lot of individual, often idiosyncratic techniques, and they're scattered about. So I don't have a great source to point you to. Implicit in the examples that I've chosen are places to go and look. So there's a collection of techniques, not just the cognitive modeling, keystroke GOMS types of techniques, but there are techniques for interacting with users through scenarios to understand what they're actually looking for. Those seem to me not to produce any very crisp identification of value. They help you as the developer understand the client better. They could sure use something. There are techniques like the techniques that Sean Butler borrowed from decision theory for eliciting better information. The problem there is that it's easy enough to go off to a user and say, are you 0.379 or 0.428 concerned about denial of service attacks? And if you press them hard, you can get an answer, but the answer doesn't mean much. What you can do is say, are you more worried about this than you are about that? And if you do that in a sufficiently systematic way, then you can derive those numbers that you can subsequently compute with. So my take is that there's a lot of individual pieces out there, but they're not systematically organized. And so I don't have a bucket that you can go and look in. And incidentally, I'm not just asking what is happening at Microsoft. I'm interested in what you know about the world that I might have missed.
I think we should probably conclude here. Let's thank Mary again.